So welcome everyone to this event in honor of the Black History Month, October. It's a pleasure to introduce Nazar Miheisi from King's College London. Naz did his undergrad already in King's College, but in engineering, and did a PhD in Leeds under the guidance of Jonathan Partington, then left academia, and then went back to academia, joined King's again, and is now at King's since 2017. Please.
Thank you, Sabine. Okay, so hopefully everyone will be able to hear me, and if not, let me know and I'll grab a mic. Yeah, so thanks a lot for the invitation. I've been wanting to come up to Durham for a while, so this is a great occasion. So yeah, thank you, Sabine. So the stuff I want to talk to you about today is basically a circle of ideas that I think are quite interesting. This will be a bit of a survey and mostly quite introductory, so I'm hoping most people will be able to get something from this because I know it's a fairly broad audience. Just by way of some caveats. So if at some point I say something that you're not sure about, please feel free to stop me. I'm going to try and explain as I go along, but yeah, do please feel free to interrupt me at any point. Also, I'm fairly new to this area, and I know that there are some people in Durham who know more than a little about this, and who are certainly more expert than me. So yeah, please chip in if you have, or keep me honest in case I say something that's not completely accurate. Okay, cool. So I'm going to use some measure theory, and maybe there are some undergraduates here or beginning graduate students who have never done any measure theory. That's fine. If you have done lots of measure theory, then you'll probably be horrified at what I'm about to say. But nonetheless, this is basically all you need to know. So for me, I'm going to be talking about the measure of a set, and I'm only going to be thinking, or if you don't know about measure theory, just think the unit interval. Everything you can work with in the unit interval. And the measure is just the probability that a randomly chosen point is in this set. That's the measure of a set. It's the size of a set. That's all. To be precise, if I have some interval, I just look at its length. That gives me the measure, okay? If I have something more arbitrary than this, so take some general set, which is not necessarily an interval, then I cover it with intervals. So I just find some intervals that cover this set, and I just sum up their lengths, and then see what's the smallest number I can get by doing this. And this gives me the size of the set, okay? So this to me is the Lebesgue measure. And I know this is not completely accurate, but you don't lose anything by assuming this. Okay. So in particular, sets of measure zero are sort of play a special role. So the key point is that these are small and exceptional and in some sense negligible, okay? So whenever we talk of sets of measure zero, these are like this very exceptional small set. This is how you should think of it. And so this terminology, which is standard, but if you're an analyst or a probabilist, is I will often say something happens almost everywhere or for almost every x to mean it happens for all x except on this small exceptional set, a set of measure zero. Okay, so that's just what this terminology means. Yeah, I don't know if someone teaches third-year measure theory or something here and is annoyed that they're going to have to undo my good work later on or something. So I apologize if that's the case. Okay, so that's basically all you need to know about measure theory for the rest of the talk. Okay, so now let me start properly. So the sort of motivation for these types of problems comes from this concept in number theory of equidistribution, which is really a fundamental concept in number theory. And if you go back, say, 120 odd years ago, there was this what's known as the equidistribution theorem. This is a fundamental theorem in number theory. And it basically says the following. If you take an irrational number and you look at the multiples, you look at this orbit, like alpha, 2 alpha, 3 alpha, so on, it's what's called uniformly distributed in the unit. And what this means is, so I'm going to take the fractional parts of each of these numbers, right? So I throw away the integer part. So if the number is 3.1567, whatever, I just take 0.1567, whatever, and I throw away the integer. So I always have a number in the unit interval. And I'm just going to count how many of them hit this interval up to some integer n. I look at some length n, and I count how many and just divide by n. So I'm looking at the frequency with which I'm hitting this interval. And I let n go to infinity. And what this says is, I just recover the length of the interval. So it's like random sampling. This sequence is basically like I'm sampling random points. If I do it enough, the number of times I expect to hit any interval is about the length of the interval. And this is what this is saying. So sampling up multiples of an irrational number kind of has this property. So it's worth noting, by the way, of course, if alpha is rational, then this sequence is periodic. So that can never happen. So this really does distinguish rationals and irrationals. Okay. So it was a few years later then that Weil proved that if you take not just all multiples of alpha, but you look at just multiples that sampled as squares. So alpha, and then you've got 2 squared alpha, 3 squared alpha, 4 squared alpha. So this is a very sparse sequence, right? I'm only sampling at very, very sparse times now along this sequence, and I still get the same property. So this is quite a remarkable theorem. And then along the same lines, I think Vinogradov, as part of his proof of the odd-Goldbach conjecture, proved actually that if you sample at primes as well, so you look at P1 alpha, P2 alpha, so on, so this would be 2 alpha, 3 alpha, 5 alpha, so on, that this also has the same property. It's also uniformly distributed mod 1. I didn't write it down, but it's not true that every sequence, you can't just choose any subsequence. So take 2 to the n alpha is not uniformly distributed mod 1. For some alpha, there is a subtlety here, but there exists alpha for which it is not. Okay. Right. So there's a natural question that comes from this. So here we looked at intervals, and you could kind of recover the size of a suitably nice set. So the natural question is, what happens if you replace this interval by an arbitrary measurable, but everything is measurable today? Take some arbitrary subset, can you recover the size of it just by sampling? Okay, so if you think about this for a moment, actually, you can't hope for a word-for-word extension. There's no way that that can be true. So why is that the case? This is a sequence, right? And any sequence has measure 0, has length 0, has no size. So I can always take the complement of it, for example, the complement of the sequence will never hit it. But that has a lot of measure, right? It has measure 1. So certainly this is not true as stated for a general set, if it's not an interval. Okay. So it took a few years actually, and then until the right generalization came. And this was a result of, well, Birkhoff and then Kinchin extended it a bit. And it says the following. Okay, so maybe this sequence does not hit E frequently enough to give me the measure. But if I just shift it a little bit, choose some X and just shift the whole sequence a bit, then actually I can do that. And in fact, the set of X for which this won't happen is negligible. So to be precise, for almost every X, this sequence is uniformly distributed mod 1, even if not for every X. Okay. And in fact, necessarily not for every. Of course, this depends on the set E, but as in the exceptional set depends on the set E, but nonetheless. So this was sort of the right generalization. So this is an example of what's called the pointwise ergodic theorem. So I'm just going to rephrase this a little bit. Oh yeah, by the way, so similar generalizations for the sequence n squared alpha and Pn alpha also exist. And they came, maybe you'll notice, actually much, much later. So, and these are really the starting point for what I'm going to talk about today. So, okay, so let me just rewrite that top line. So I'm just going to set f to be the characteristic function. So this is the indicator function of this set. So this is 1 if x is in this set and 0 otherwise. Then this expression here is exactly, I'm just looking at, oh, sorry, this should be x plus n alpha. Yeah, my bad. That's, okay, the first typo already. So this should be x plus n alpha. And I'm just taking an average of this, right? And then on the right-hand side, I have the length of the interval, which is exactly its integral. So both sides of this are linear in f. So I can take linear combinations of characteristic functions and it's still true. And then if you think a little bit harder, with some approximation, I can approximate, okay, this requires some stuff, but you can approximate any bounded function with a finite linear combination of characteristic functions uniformly. And so actually, okay, it's not completely immediate because the exceptional set depends on the characteristic function. So you have to be a little bit careful when you do this approximation. But nonetheless, it's not so difficult to show. You can replace f with any bounded function, and this is true. What is a bit of a miracle is that actually you can take it to be any integrable function. And that is not clear at all. And in fact, this was the thing that Pynchon sort of added to this. But that was, and that's really not clear, that actually you can take f to be any integrable function. Okay. So this prompts the question. So now what we're interested in, sort of motivated by looking at these versions, you know, so you could ask, well, okay, let's take this. So Bourgain proves that n squared alpha has this property that x plus n squared alpha is uniformly distributed for almost every x. You can ask, well, can I take f? Can I do the same thing but plug in any integrable function? Turns out the answer is no for each of these two, but I'll sort of come on to this. Or more generally, you could talk about weighted averages. You could look at other weights that are interesting and ask what happens, whether you have any sort of convergence. So I guess the question that I kind of got a little bit interested in recently is as follows. So if I give you a sequence, and for the moment, we can allow it to be complex value. When do these converge almost everywhere? And basically, I'm just waiting. Again, this should be x plus, of course. I'm waiting here by this function, and I'm dividing by the running total. So this really is like an average, okay? And if I do have convergence, then for what class of functions? I mean, is it just bounded functions? Can I extend it to sort of functions that have some kind of singularities and so on? That's kind of the question. Okay. All right. Does anyone have any questions before I move on? Oh, perfect. Yeah, go ahead.
Yeah. So, your question did not make a lot of sense. Why do you allow yourself to consider almost every x and not almost every irrational alpha?
So you can do that. I guess, yeah, it depends on the question you're looking at. So, for example, what I said earlier about taking the sequence 2 to the n, it's true that for almost every alpha, 2 to the n alpha will be uniformly distributed. I guess that it's a matter of perspective, and the perspective here is you're looking at iterating a single map. And the map that I'm thinking of is adding alpha, basically. So my alpha is fixed. So I've got a fixed transformation. I guess historically where it came from, ergodic theory really is you have some transformation of your phase space or whatever, and you're looking at the dynamics that influence of this math. In principle, so looking at different alpha is like looking at a class of maps and asking what happens kind of uniformly across this class, or in some sense. Yeah, it's a good question.
What if X is not?
Sorry?
What if X equals alpha?
What if X equals alpha? But so alpha is fixed here, right? And X can be whatever. But the point is, yeah, X is. So yeah, okay, maybe I should say. So I don't know what the bad set of X is for which this does not hold X. All I know is that it's small, right? And what it's saying is if I choose an X randomly, it will, with probability 1, work. But I can't say anything about an individual X. I can't say if I choose X to be 2/3, then typically at least, you know, these theorems say nothing about that, the convergence of a single one. Did that answer your question?
Example, alpha 6.
Sort of, yeah. So alpha is, yes, X and alpha is fixed. Maybe this is the best I could think about it. Yeah. Anything else? Cool. Okay. So now let me state this a bit more generally, which is measure preserving systems. So again, if you haven't done measure theory, you can ignore most of this. You really don't lose very much by just thinking of the example I just gave, okay? This example is completely sufficient for everything I'm going to say, but I'll just state it more generally for those people that maybe have some background in this. So for me, a measure preserving system is just a measure space, sigma finite, and a measure preserving transformation. If you know what those words mean, that's fantastic. If you don't, please don't worry. Just think about the examples I'm about to give. The first example is the one we just discussed. So my space is the interval 0 to 1. This measure is just my way of assigning size, and that's just the length or the Lebesgue measure, which is what we just described. And my transformation is just add alpha and go and look mod 1. So throw away the integer 1. Yeah? So this is exactly what we just discussed. And so this is a perfectly good system. And in fact, this is the archetypal example. So if anything, if you're not happy thinking about the abstract setting, this is the picture you should have in your mind, and this is completely fine. The other very important example, hopefully I can explain why, is you take all the integers, your measure now, your size is just counting the number of elements in a set, and you just shift, your transformation just shifts by 1. Okay, so this is just the integer shift system. So these are the two by far most important cases. You could also look, for example, at doing a shift mod n on the finite group. And just to convince you that there is more than just these examples, is also, this is a nice example, the doubling system. So you just take the unit interval again, usual Lebesgue measure again, and you just do 2x, you double it, and then work mod 1. And this is quite an interesting system with very interesting properties as well. And there are many, many others that come up sort of naturally, that just sort of appear in the wild. Okay, so for the most part, I'm always going to assume that the measure is finite. So something like the unit interval, but the total mass is 1, or mod n. So this system is particularly important, but in most of the times I'm speaking, unless I say otherwise, I'll think it's finite. Be working in the finite setting. Okay. So before I actually state some kind of, results about these measure preserving systems, I'm just going to digress a little bit and talk about a slightly parallel circle of ideas, which is topological systems. So this is sort of a subclass almost, where we don't have a measure as such now, but now we're going to insist that we're working on what's called a metric space. So again, you can think the unit interval or some subset thereof. And now our map is continuous. So it doesn't preserve the measure anymore, but it's continuous. So the concepts that people typically look at here are what's called minimality. So a set is minimal if this transformation leaves it fixed. So if you start in A, you get back to A, and there's no subset which is also invariant. So it's the smallest. So it is minimal in this set. So this is sort of one of the main concepts. And the other is recurrence. And so a point is recurrent if basically, if you look at its orbit, you look at the iterates, if it gets arbitrarily close to where it started at some point. This is what recurrence means. So for example, for the irrational rotation map that we looked at, the whole set is minimal. Okay, the whole interval is minimal. It has no invariant subsets. And also every point is recurrent. So there's a theorem of Birkhoff which says if your space is compact, so for example, if it is, say, the unit interval, and for those of you who've noticed that I'm taking sort of might say this is not compact, we're identifying the endpoints, so really you should think of it as a circle rather than an interval. Then it contains a minimal set and has at least one recurrent point. So this is a theorem. So there's a question which I could not really trace back so much. So some people claim it was Gotch, who is like one sort of a big figure in topological dynamics at some point. But I couldn't really find the original source of this question. But anyway, it was one that was asked of me. And the question was, is it possible that every point is recurrent, but you have no minimal sets? So, okay, necessarily it can't be compact. And this was open for quite some time. And then it was finally settled by a guy called Scott Williams in a very obscure paper where he basically, well, he shows in a semi-constructive way that the answer is yes. So he cooks up this example on the irrationals, such that every point is recurrent, but you have no minimal sets. So you look at, which is kind of weird, you take the orbit of any point, right? And you look at its closure. This is an invariant set. It tells you that there is necessarily another point, you take its orbit, and this is a strictly smaller set, and you can keep doing this. So there are no minimal sets at all. So this is kind of a remarkable counterexample. And so I mentioned this, I wanted to kind of highlight some particular mathematicians, in particular some Black mathematicians that put some really interesting stuff. And Scott Williams is one of them. So he's a professor, I think, in New York. I don't know if anyone has sort of come across his stuff. He's really a topologist. So I came across this example and I looked him up, and he's like quite an interesting character. And he really works on more topology, set theory, sort of things that are close to logic. But he comes up with some very ingenious counterexamples. And he also really tries to promote sort of minority students and sort of minorities in mathematics. He co-founded this thing called the Committee for African and American Researchers in the Mathematical Sciences. It's now, I think, called the Council for African American Researchers in the Mathematical Sciences. And it's still going. They still have like conferences every year and stuff. So it's quite an achievement. Yeah, he's not so active now, but he's done some quite interesting stuff in sort of point set topology and so on. Okay, so yeah, I quite like this guy. Cool. So right, let me jump back to what I want to actually, the stuff that is closer to what I'm interested in. So to do this, I need to do another quick crash course on some analysis. Okay, and then I will state an actual result. So LP spaces, so I'm only going to think about the unit interval. If you know what they are more generally, that's great. So it's just functions. You define this sort of LP norm by just taking the integral of the p power of the function of the unit interval. And for p equals infinity, you just take the supremum over the function interval, okay? And LP is just the function for which this is finite. So L infinity is the bounded functions, L1 is the integrable functions, and LP sits somewhere in between. So in particular, you have these sort of chain of inclusions. So this is how you should think about it, basically. L infinity is nice and bounded, and as you get closer to 1, the singularities get worse. So p equals 1, if you sort of squint, if you really squint at a function in L1, then the singularity can look like 1 over x. I mean, it's not quite 1 over x, but essentially like 1 over x. And so they're quite bad singularities, whereas for some intermediate p, it's like 1 over p or something, 1 over x to 1 over p. So for large p, it's almost bounded. The set on which it's large has to be small. So so it's easier to have convergence for functions here than it is here. That's the main point, okay? And so little LP is the same, but we define it in terms of sequences, so the integrals become sums. It does not have this property, by the way, but it's the other way around now. Okay. All right. So the pointwise ergodic theorem, which is basically the theorem we stated earlier, just says for any measure preserving system, again, if you're not happy with that is, just think irrational rotation, and any integrable function, then I sample the function on this orbit, and this converges for almost every x. And it can be averages. And okay, so also we know that if it's what's called ergodic, then the limit is actually equal to the integral of the function. If you don't know what ergodic means, don't worry, it actually won't really feature in what I'm about to say. You can take this as the definition of ergodic. It's the equivalent. Okay. So let's generalize this concept. So this is a definition, I think, that goes back to Bourgain, but it's now stuck. So sequences are called universally LP good if for any measure preserving system and any function in LP, you get convergence of these weighted averages. Pointwise, almost everywhere convergence. So just to note a comment about this universally LP good, there are some that are good for some systems and bad for others, which is where the universal comes from. Universal means for all measure preserving systems. And so the pointwise ergodic theorem is basically the statement that the sequence which is constantly equal to 1 is universally L1 good. That's a rephrasing.
For this definition, we don't need everybody's LP.
No. Yeah, exactly. So you just need measure preserving. So in general, by the way, the limit is not the integral, even if it's ergodic. Even in the case that the transformation is ergodic, it doesn't necessarily have to equal to the integral of the function anymore in general. For the irrational rotation, it usually does. In most of the examples that we're thinking of, it typically does for separate reasons. And as I said before, it's easier to be L1 good than it is to be, harder to be L1 good than it is to be LP good or L infinity good. Okay. Okay, so now I'm just going to run through a few examples and let you know some of the results that we have that are interesting, I think, or the results that are known. So, as I said before, the squares, the indicator function of the squares is universally LP good for all p strictly bigger than 1. So this is a deep theorem of Bourgain that sort of started off all of this. By the way, you can replace n squared here by the orbit of any polynomial with integer coefficients. So any polynomial that takes integer values of the integers the same is true. It's also true for the primes. This exactly the same result happens for the primes. So this goes back to Bourgain. He proved, I think, for p bigger than, I think, 1 plus root 3 over 2 or something like this. And then Werdel got it down to p bigger than 1. But then there was actually a mistake in his proof, which was corrected by Marius Smurek and Trojan in 2015 or something like this. But their idea was basically correct, I think. And just to note, the convergence along the primes is roughly the same as weighting it by something called the von Mangold function, if you know what that is. So it's completely equivalent. They have the same okay. The next example, which is maybe of interest to number theorists more, is this Mobius function. So this is, yeah. That's a good question. I'm going to come on to this hopefully in a few minutes. So, okay, I'll tell you the punchline. It does not converge with p equals 1. And in fact, it fails quite badly. But that's quite a theorem. Yeah, that was an open problem for a while. But yeah. But I'll try to say something about this. Okay, so the Mobius function basically is 0 if you're divisible by a square number. And then minus, it just counts basically the number of distinct prime factors. There's only 0 unless you're square free. If you have an odd number of prime factors, it's -1. And if you have an even number of prime factors, it's 1. So it's just plus or minus 1. That's it, just depending on whether you have an odd or even number of prime factors. So this is universally L1 good. So it's proved all the way down to p equals 1. So just to note this, if you just restrict yourself to systems that have one point, where x consists of a single point, so the only functions are constant, then the convergence on those systems is equivalent to the prime number theorem. And if you restrict to systems that have finitely many points, so the integers mod n, then that's equivalent to the prime number theorem on arithmetic progressions as well. So that's or Dirichlet's theorem. It's completely equivalent. And there's a deep conjecture in number theory called the Sarnak conjecture, which says, I'm not going to define what low complexity means. If you know, okay, so it means 0 entropy, so it's a system of 0 entropy. If you know what that is, great, but don't worry too much. But for certain nice systems of sufficiently low complexity and continuous functions, you get convergence for every x. The difference between this statement and this statement is this is for almost every embedded in this, and this one is for every for suitably nice systems. So this is like an almost everywhere version of the Sarnak conjecture. That makes it seem like it's close. The difference between almost every and everywhere is vast. This is easy to prove because you can, yeah, this is not a hard proof. Okay, assuming some very hard things in number theory, but if you have the prime number theorem and some estimates that are well known, this is really not hard to prove, and it almost follows directly from the normal Ergodic theorem. This is wide open. I mean, it's been proved for a few systems like the irrational rotation and so on, but as far as I know, it's not really that within reach. But I don't know if maybe there are number theorists here that probably can tell me about this. Okay. The other example, so the example that I'm really interested in or have been interested in is the divisor function. So this basically just counts the number of divisors up of n, okay? So the way you should think about this, like the von Mangold function was sampling primes, this is like averaging over highly composite numbers or something. And this kind of has some peculiar sort of complexities because it's highly oscillatory, and also it has many, many level sets. So for large n, you know, if you're prime, you have 2 divisors. But you can also have up to, say, n to the epsilon divisors and everything in between. And it's very, very erratic. So if you think about it like you're equating it to something on the real line, it would be like a singular measure or something, singular configuration like this, discrete analog of this. So it has its own challenges. So this seems like an interesting case. So actually, this was proved by Cooney and Weber in 2017 that this is universally LP good for every P. So just a comment. So there's a more recent version from this year of Christina Giannazzi, me and Hamid Masavi, who's in Bristol. She's in Vanderbilt at the moment. So we give a different proof of this with some slightly sort of stronger quantitative estimates, and also just an extension to the Gaussian integers as well, and also some other quadratic number fields. So the last example I kind of want to discuss in detail is this, what's called Wiener-Wintner theorem. So here you take an exponential. This is not sort of an arithmetic example, but you just weight it with an exponential, complex exponential. Then you don't have to try so hard. You just apply the pointwise ergodic theorem to a slightly larger system. And what you get is that this is universally L1 good. This weight is universally L1 good for any possible choice of theta. The problem you have is that the exceptional set you have for each theta, you can, in principle, can be different. It turns out, actually, that you have this Wiener-Wintner theorem, which tells you that, in fact, for any f in L1, there exists a single set of measure 0, such that for every theta, you have convergence. So this is quite a deep theorem. And so, yeah, the miracle of this theorem is that there is one measure 0 set that works for all theta. And there's no reason to sort of see why this is the case. Now there's lots of proofs of this, although the original proof of Wiener and Wintner had a mistake in it, I think so. So a really nice extension to this. So sorry, there's a little bit of technical stuff in here, so don't worry if you don't get all the details. That if you actually, this is the unique invariant measure for T, so a bit like the irrational rotation, and you have some other cancellation condition on F, so don't worry about that. Then actually this convergence is uniform in X and in theta under these conditions. So if you have some extra assumptions, and so this is a very deep theorem. And in particular, it lets me talk about Idris Hassani, who's like a hero of mine. So probably more than anyone else, apart from maybe Bourgain, that I'm going to mention today, he's contributed more to this circle of ideas. And I think he's really exceptional. He's actually a Beninese mathematician. I suspect he works well, now at Chapel Hill. And so he has done some really amazing stuff, actually, in ergodic theory and harmonic analysis, probability theory. And he's written a book about these Wiener-Wintner ergodic theorems and various other quite spectacular theory. I couldn't resist but show you this theorem, which is not directly related to what I'm saying, but it's one of my favorites. And by the way, I should just say these multilinear ergodic theorems are very, very hard to come by. And what he looked at is basically if you take, say, a box, imagine Mn and M plus N and 0. This forms the corners of a box. And you look at all possible boxes contained in this box of size n, and you average over that and let n go to infinity. So this was an open problem before. The mean convergence was established before this. And this is only a special case, by the way. Even this was open. I thought this theorem was really amazing. So I just thought I'd show it to you. Actually, he had a very weird experience when he moved to UNC. He's been there for a long time. He moved there in like the 80s. But then initially, despite sort of doing some very outstanding stuff, they would not make him tenure. And so it turned into a protracted legal battle. And then he won, and they gave him a tenure position. Then they reviewed his case after this. And then a year later, he was promoted to full professor. And he still remains the only person in the history of this institution to be promoted from associate professor to full professor within 1 year. But that's because they felt it was overdue. I think when they looked at what he'd what he'd actually accomplished. But nonetheless, he is really a real major contributor in this area. Okay. So, to your question, which is about the endpoint, what happens at p=1? So we saw that these are the divisor function, the characteristic function, the squares, the primes, they're all LP good for p bigger than 1. And that's a very natural question. And this was sort of a notoriously complicated question. So Vitaly Bergelson, who's like one of the godfathers of this area, at one point said that this is sort of one of the central open problems in ergodic theory. And then much more recently, so Cooney-Weber, who proved the case of the divisor function, wrote, which I thought was quite curious in their paper. They put this as an open problem and wrote, we strongly believe that, well, they referenced their theorem, but the point was ergodic theorem is no longer true in L1. And we think the proof of this should be very difficult or something. So I don't know if that meant that they couldn't be bothered to try or what they tried. I'm not sure. Probably the former. So, okay, to kind of give the results properly, I'll kind of give you another definition, which is as bad sequences or bad weights. So we'll say that the sequence is universally LP bad if every measure preserving system, you can find some function such that this fails to converge almost everywhere. So it diverges on a set of positive measures. Yes. So this is a bad sequence. So just to note, there's a big gap between universally good and universally bad, because some things are bad for some systems and good for others. So this is not just that it fails to be good. This is really much worse. And also, just to note that there exist weights that if I give you any p, there exist weights that are LP bad, but good for LQ for any q bigger than that. Okay, so this is much, yeah. Right, so what do we know about the endpoint? So now all of those questions have actually been settled. So the real breakthrough result was of Butzelich and Molden in 2008. So they proved that the squares were universally L1 bad, the characteristic function of the squares. And this was really an amazing result. This is like this paper, it's like this really intricate construction, and it's really ingenious. I mean, I want to say it's a lovely paper, but it's also, to some extent, quite unreadable. But it's still very ingenious. Then a few years later, Patrick Lavictoire was able to do the same thing for the primes and for kth powers. So this result was just for the squares. It was really, I went quite rigid for the squares, and he was able to do kth powers and the primes and show that they're universally L1 bad. And it's based on the same idea, but again, he really had to do a lot of work. Then, so this year with Christina and Hamid, we were able to show that the divisor function is universally L1 bad. Well, so this is all based on the same idea. It's all based on this very intricate and very ingenious idea of Butzelich and Molden. And with each step, it becomes a little less intricate and a little less ingenious, and people see how to make it slightly more general, make it fit other things, and so on. So it's still not completely straightforward. So, for example, if you take a general polynomial orbit, which is LP good for all p bigger than 1, just as the squares, none of these cases cover a general polynomial orbit. So, yeah, I don't know. So there's still a lot to figure out. Okay, so I think okay, so I'll say a couple of words about how these things. I kind of want to give some indication as to how you get some of these results. And it's basically comes down to a lot of sort of harmonic analysis. And it's all based on two principles, really. So the first principle is, in fact, what I'll do actually, since I think we've got what, a few minutes left, right? 5-ish minutes. Okay. So I'll say a couple of words and then I'll just mention one or two mathematicians who kind of contributed. No, in fact, I will just do that. So I will skip some of this, and I will. Sorry, that was not the interesting part, so it's fine. They're not missing anything, and I will go straight to this guy. So he is a very interesting character. He's actually a mathematician and an inventor. So the reason I wanted to mention him is because he's sort of done a lot of work on what's called maximal functions and did some generalizations of things like the Hardy-Littlewood maximal inequality. And these are a lot of the tools that we use to prove pointwise convergence. It's all estimates for maximal functions. And he was kind of a contributor in this. And he basically, so he, as far as I know, I think he's published more papers than any other Black mathematician. And including this book, which some people may have seen already on integral operators. And he actually tried to, in 1981, he created his own journal called the Bulletin of Mathematics. It didn't last long. It sort of until about 1986. And as far as I can tell, he's the only person who published in it. So it didn't completely catch on. So he was actually, but he is very influential. He did a lot of stuff. And then he was at the University of Sussex and then at East Anglia. And he also got very frustrated that he was not being promoted despite having published over 30 papers in the previous 10 years and written this book. And they refused to promote him, so he quit and decided to just focus on his inventions. And he tried to invent all sorts of things, and he's got a whole bunch of patents. I don't think anything's really taken off. But he's a very interesting character. Then he made this journal. But yeah, nonetheless, he did some very, very good mathematics as well. So he's definitely, and so this picture, there's not many pictures of him. This is from, I don't know if anyone's seen the Princeton Companion to Mathematics, this book, and it has a load of mathematicians in it, mostly Fields medalists. And so he's included as one of this list of Fields medalists. He's like next to Jean-Pierre Serre or something. And his daughter actually is also a mathematician and also on the same lineup, I think next to Alain Cohen. So his daughter is does geometric analysis, which is rare for mathematicians to have.
Pete,
Yes.
I was in a grad student office with them.
Oh, really? Oh, okay, great.
Yeah.
Oh, amazing. Oh, yeah. Oh, cool. And so, very quickly then, one other person who I think is pretty outstanding. Sorry, are we done? Okay, so Raymond Johnson. If you want to know about him, I'll tell you about him. I guess probably that's a scientist to stop. So maybe I'll stop there. Thanks.